Hi guys, welcome to 6.3 sampling distributions for proportions. So we're going to talk about what they are, we're going to go over the notation and the formulas or formulae, and then we'll go over a couple of example problems. All right, so first off, this is what's going on. So there's three different distributions involved with these sampling distributions. First, we've got the population distribution. So say for some population, we're split evenly between blue and red. People with favorite color blue, people with favorite color red, whatever. So our proportion that favor blue, say, I think blue is what we're, no, looks like we're going with red. Proportion that favor red, say, would be 50%. Right, that's our population proportion. That's our parameter P. All right, then we take samples, random samples, all of which are the same size 20, and we get all these different samples. Now, notice none of them are 50-50 again, because, it's not likely we're going to get exactly the same when we're taking a random sample. Like this one had 8 reds, and this one has, looks like 11 red, and this one has, looks like 13 red. All right, so we would say P hat, that's the sample proportion. So if we're working with a sample, we get a little headgear. It's called P hat. This would be 8 out of 20, or 0.40. And this would be 11 out of 20, or 0.55. And this would be 13 out of 20, or 0.65. And if we take all possible samples with the same size 20, that gives us what's called our sampling distribution. And all of these are different P hats. Like this is just one sample value here. This is one sample value. This right here is a whole bunch of sample values. All right. And right here in the middle, 0.5 is the mean of all the P hats, or the mean of the sampling distribution, which happens to be this mean right there, 0.5, 0.5. All right, so we've got our population distribution with proportion P, we've got our samples with proportions P hat, and then we have our sampling distribution with right in the middle, the mean of the P hats. All right, so this slide basically just covers that again. So P hat, sample proportion, S, standard deviation still, P, population proportion, sigma, standard deviation for the population. All right, the mean of the P hats is the mean of the sampling distribution of P hats, and the standard deviation of the P hats is sigma P hat. All right, now the formula is here, so when we're working with proportions instead of means, so this is different, like our P's will be percents or decimals, the mean is just the population proportion. All right, population proportion, P. That is the middle of the sampling distribution, the mean of the sampling distribution. All right, the standard deviation of the sampling distribution. Well, it works just like a binomial distribution where P is our proportion. So we take this standard deviation, the binomial standard deviation, and we divide the whole thing by n. And what it ends up simplifying to look like is this. So the n on top cancels, and we still have an n now under the square root. All right, it's really the square root of n squared like that, and one of these n cancels and leaves us with this guy right here. So there is our formula for the standard deviation, is the square root of P times 1 minus P over n. All right, now last time we had a couple different things to make us normal. Here we only have one. So we have, really it's two conditions, but there's only one way to be normal. N times P needs to be greater than or equal to 10. And n times 1 minus P also needs to be greater than or equal to 10. If both of those are satisfied, then we get that our sampling distribution is normal, and we can use inverse norm and normal CDF to do a whole bunch of fun things. All right, so here's an example of what the problems are going to look like. So the proportion of women at a school is 55%. So 55% are women. That is a P, population proportion. Researchers would like to take a sample of 200 students. Well, that looks like our sample size, n, 200. From the school to see how they feel about the name of a new building. What is the probability of getting less than 50% women in the sample? All right, so one way to do this is to say, okay, well, is this going to be a normal distribution? Is these samples all going to be normal? So we need to check n times P, so 200 times 0.55, and 200 times 1 minus 0.55, which is 0.45. And we need to see what both of those are equal to. So this is going to be 110, and this is going to be 90. You can type that in your calculator if you want. But both of those are greater than or equal to 10. So both of those check out, and that means we are going to have a normal sampling distribution. So now we need to know what's the mean of that sampling distribution. Well, the mean of all the p hats is going to be the 0.55. Now, what's the standard deviation of that sampling distribution? Well, it's the square root of p, 0.55, times 1 minus p over 200, the sample size. Now, I don't know that one off the top of my head, so pulling out my trusty friend, the calculator. And let's see, we've got second, I'll get out of this, quit. Second square root, 0.55 times 1 minus 0.55, close parentheses, divided by 200. Notice all of it's under the square root. 0.035. Don't forget that 0. That's important. 0.035. All right, so now we've got a mean and a standard deviation. Now we want to know what's the probability of getting less than 50% women. All right, so now it gets a little tougher to tell the difference between when is it normal CDF and when is it inverse norm. All right, so in the middle of our sample here is 55%, or 0.55. Now we want to know the probability of being less than 0.50, less than 50%. All right, so that's what's going on here. So that tells us we want normal CDF. The less than is kind of what tells us that we're using normal CDF. So normal CDF, our lower bound would be like 0. We get down to 0% down here. Our upper bound would be the 0.50. The mean is the 0.55. And the standard deviation is 0.035. So everything here is decimals. That's pretty common here. All right, so normal CDF, we're going from 0 to 0.50. 0.55 is our mean, and 0.035 is our standard deviation. There's our normal CDF, and 0.0765. All right, so what's the probability of getting less than 50% women in our sample? About 7.6%, or 0.0765. All right, so it looks like maybe 82 to 83% of samples will be 50% women or more. All right, so that's the first problem here. The next problem, same situation. So we still got the 55%, we still got the 200. Now they're asking a different question altogether. So what would be the proportion of women sampled in the top 5% of samples? All right, so we're still using this mean, we're still using this standard deviation. Now we're asking about the top 5% of samples. So here would be the top 5%, 0.05. All right, the mean is still the 0.55. What percent would we be at here to be the top 5%? Well, remember we need to know what's to the left of this if we're going to use inverse norm. So we get 0.95. We are using inverse norm. So if we see top 5% or top 10% or bottom 5% or bottom 10%, so it's like the top and bottom is what's giving this away here. All right, or if we see middle 50%. All right, so let's see, we got 95% here. The mean is still the 0.55. The standard deviation is still the standard deviation we calculate over here, 0.035. And now we can see what percent would be the top. It's going to be close to 55 because that was close to 5%. So inverse norm, 95% below, so 0.95 for our area, 0.55 for our mean, and 0.035 for the standard deviation we calculated. And we get 0.6075. So that'd be 60.75%. All right, so the top 5% of samples will have 60.75% women or more than that. All right, let's try another example. So we'll switch up some colors here. All right, so the proportion of independent voters in a town is 30%. There's our P, 0.30. Pollsters would like to take a sample of 400. There's our sample size, 400. People from the town to see how they feel about an upcoming election. What is the probability that more than 33% of those selected will be independent? All right, so first off, we need to check, is this going to be a normal sampling distribution? So we get 400 times 0.30 and 400 times 1 minus 0.30. So let's say that's 30 times 4 is 120. And then 400 minus 120 is going to be 280. And both of those are greater than or equal to 10. Again, you could just type both of those into your calculator and get answers. That's fine. So that tells us that we are going to work with a normal sampling distribution. The mean of the sampling distribution is just this 0.30. The standard deviation of the sampling distribution is the square root of 0.30 p times 1 minus p, so 1 minus 0.30, over our sample size, 400. All right, as this keeps getting bigger, these standard deviations will get smaller. Oops, one too far. All right, so let's see, second square root, 0.30 times 1 minus 0.30 divided by 400. 400, not 40, there we go. 0.0229. 0.229, there's our standard deviation. So now we want to be more than 33%. So we take a look at our normal distribution here, which we found out it's normal. The mean is 0.30. 33% would be somewhere up above it here. And we want to be above that, more than 33. So we want to know this area. Well, if we want to know this area, or this probability, that's normal CDF. All right, it says, what is the probability? That tells us for sure it's normal CDF. All right, the lower bound here is the 0.33. The upper bound here is something big. I mean, you can go to 1 or you can go up to like 100 or something. The mean is 0.30. The standard deviation, we calculated to be 0.0229. Don't forget the 0 in there. I see some of you like to leave out the zeros when we're doing work here, so don't leave out the zeros. Zeros are important. So we get, let's see, lower bound was 0.33. Upper bound is something big. 0.30 for a mean and 0.0229. And we get 0.095. So 9.5% is what that would work out to as a percent, or we can just say 0.095 is the probability of having 33 or more. So almost 10% of samples will have 33 or more independence. All right, last one here. So same information for the top here. New question is, what would be the proportion of independent voters in the bottom 5%? All right, so we're asking about the bottom or top 5%. That tells us that we should be doing inverse norm. All right, so if we take a look at the graph, I always like to look at the graphs, with our mean of 0.30, same mean, same standard deviation we had over here, and we want to be in the bottom 5%. So that means this area down here is going to be 5, and yeah, sure enough, this up here would be the 95. We're not going to use that though, because when we're trying to find this x value, we look to the left, and that's the 0.05. So the area is the 0.05 because it's below, it's the bottom. The mean is still the 0.30. The standard deviation is still the 0.0229. All right, so we throw that into our calculator, second distribution, inverse norm. So 0.05, 0.30, and 0.0229. And we get 0.26. All right, so this is 0.26 is our answer, or like 26%. So what would be the proportion of independent voters? 26% of them. So if we're doing the bottom 5% of samples, if it's 26% or less, that would be in the bottom 5% of samples. And that's our answer. All right, so that's it for this one. So that's a couple of examples there. If you need to rewatch. Make sure you upload the notes, and the homework is shorter this time. It's half as long. So please get the homework done.